The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I'll respond as soon as I can. Alrighty, so today we're going to go on to section 9.4. But first, I had some requests from you students, so we'll get to those. This is from, let's see here, section 9.3, number 32. It says, simplify the expression if possible. All variables represent positive real numbers, so we don't need to worry about absolute value bars. If the expression cannot be simplified, enter the given expression. All right, we have the fourth root of 432 p to the 16th q to the third. All right, if we take 432 and break it down into prime factors, that's 2 times 100, nope, not 100, that's 2 times 216, which is 2 times 2 times 108, which is 2 times 2 times 2 times 54, which is 2 times 2 times 2 times 2 times 27, which is 2 times 2 times 2 times 2 times 3 times 9, or 2 times 2 times 2 times 2 times 3 times 3 times 3, which is 2 to the 4th times 3 to the 3rd. Okay. So I'm going to take the fourth root of 432 p to the 16th q to the 3rd and write it as 2 to the 4th times 3 to the 3rd times p to the 16th times q cubed. Now, p to the 16th, 16 is a multiple of 4, so that's going to come out nicely. Q to the 3rd, the exponent, the 3 is less than the index, so that's going to be stuck inside. So let's see what I can do. The fourth root of 2 to the 4th power would be 2 on the outside of the radical. 3 cubed can't go anywhere. P to the 16th, take the fourth root, would be p to the 4th power outside, and q cubed can't go anywhere. Okay. So I'm going to have 2 p to the 4th root of 27 q cubed. Any questions about that particular problem? Okay, that takes us to, again, section 9.3, number 36. Simplify the expression if possible. The variable represents a positive real number. If the expression cannot be simplified, enter the given expression. And so variables are positive, so we don't have to worry about absolute value bars. We have the cube root of 32y plus the cube root of 256y. Well, 32 is 2 times 16, which is 2 times 2 times 8, which is 2 times 2 times 2 times 4, 2 times 2 times 2 times 2 times 2, which is 2 to the 5th power, which is 2 cubed times 2 squared. Okay. So this gives me the cube root of 2 cubed times 2 squared times y. The cube root of 2 cubed is 2 outside, and I'm left with the cube root of 2 squared, or 4y. Okay, now let's deal with that second one, 256. 256 is 2 times 128, which is 2 times 2 times 64, which is 2 times 2 times 8 times 8, which is 2 times 2, and then 8 is 2 times 2 times 2, and 8 is 2 times 2 times 2, and I have 1, 2, 3, 4, 5, 6, 2 to the 8th power. And I'm going to write that as the cube root of 2 to the 6th power times 2 squared times y. And why did I take 2 to the 8th and break it apart as 2 to the 6th times 2 to the 2nd? because the 6 is the highest multiple of 3 that is less than or equal to the 2 to the 8th power. Okay, so now I have 2 cube roots of 4y plus the cube root of 2 to the 6th would be what? 2 to the 2nd power. And then I have this left inside. So I've got 2 cube roots of 4y plus 4 cube roots of 4y. So now these are like radicals, and I would get 6 cube roots of 4y as my final answer. Any questions about that process at all? Okay, I'll give you a minute to finish writing that down. So again, we're taking the radicand, the stuff inside, and breaking it down into powers that are either equal to the index or multiples of the index, and then anything less than the index are left inside. Okay, next problem. This is, again, from 9.3, number 37, part A. Simplify each expression if possible. We have the square root of 2 plus the square root of 98. Well, 98 is 2 times 49, which is 2 times 7 times 7, or 2 times 7 squared. The square root of 2 is just that. The square root of 98 could be 7 squared times 2 inside. So now I've got the square root of 2 plus the square root of 7 squared is a 7 outside with the square root of 2 inside. So I have 1 square root of 2 plus 1 square root of 2 plus 7 square roots of 2 is 8 square roots of 2. Don't forget there's an implied 1 out in front of that square root of 2. Okay, and then we've got problem number 38. We good to go on? Yep, okay. So this is 9.3, number 38. Part A, simplify each expression. The variable represents a positive real number. We have x times the cube root of 64 x to the 6th minus x times the cube root of x to the 6th. All right, well, 64 is 4 times 16, or 4 times 4 times 4, or 4 cubed. So I could rewrite this as x cube root of 4 cubed x to the 6th minus x cube root of x to the 6th. Simplifying the first radical, I have an x already. The cube root of 4 cubed is a 4 outside. The cube root of x to the 6th would be x squared outside. So then I've got what? 4x cubed, combining those. And then here, the cube root of x to the 6th would be x squared outside. So that's x cubed. So I've got 4x cubed minus x cubed, which is 3x cubed. So that's the answer to number 38, part A. And now we're going to take a look at number 38, part B. If I'm going too fast and you need me to backtrack or go slower, please let me know. 38, part B, I've got the x, let's see, x times the square root of 64x to the 6th minus x times the square root of x to the 6th. Okay. So we have an x outside. The square root of 64 is 8. The square root of x to the 6th would be x cubed. So this is 8x to the 4th. I've got an x outside. The square root of x to the 6th would be x to the 3rd. So this is x to the 4th. So 8x to the 4th minus 1x to the 4th is 7x to the 4th. So we change the index, which gives us a different answer. Okay, let's see here. I need to pull up some other problems. A different student had some questions. So let's see. Okay. These are all also from section 9.3. All right. So this is still from 9.3. This is number 16. It says, simplify the expression. The variable represents a positive real number. And we have the cube root of 216y to the 8th divided by the cube root of 8y squared. So we have a fraction and both radicals have the same index. So I could rewrite them as a single radical with a fraction inside, 216y to the 8th over 8y squared, which would be the cube root of, let's see, if we take 216 divided by 8, we get 27. And y to the 8th over y squared would be y to the 6th. Well, 27 is a cube. The cube root of 27 is a 3 outside. And the cube root of y to the 6th is y squared outside. So our final answer is 3y squared. Okay, that takes us down to number 30. And so again, this is 9.3, number 30. It says simplify the radical expression. Again, all variables represent positive real numbers. So here we have the cube root of 11a squared over 216 b to the 6th. In this case, we're going to pull them apart. And let's see here. We're going to go the cube root of 11a squared over the cube root of 216b to the 6th. Well, I can't do anything with the cube root of 11 or the cube root of a squared. However, 216, let's see, 216 is 2 times 108, is 2 times 2 times 54, 2 times 2 times 2 times 27. So it's 2 cubed times 3 times 3 times 3 for 27. So 2 cubed, 3 cubed, okay? So the cube root of 2 cubed times 3 cubed times b to the 6th. So the numerator is the cube root of 11 squared. The denominator, the cube root of 2 cubed is a 2 outside the radical. The cube root of 3 cubed is a 3 outside the radical. And the cube root of b to the 6th is b squared outside the radical. So our final answer is the cube root of 11a squared over 6b squared. And that 6b squared is under the fraction bar, but it's not inside of a radical. Okay. That takes us to number 36. We said 36, but it looks like they missed 35. I'm going to do 35 and hope that it's what they wanted. Maybe I wrote it down wrong. Anyway, 35. Simplify the expression. If possible, the variable represents a positive real number. I have the 5th root of 243 r to the 22nd power. All right, 243 is 3 times 81, which is 3 times 9 times 9, which is 3 times 3 times 3 times 3 times 3, which is 3 to the 5th power. So I'm going to rewrite this as 3 to the 5th power times r to the 20th power times r squared. Now, why did I take r to the 20th power, 22nd power and pull it apart, r to the 20th times r squared? Because 20 is a multiple of the index 5. It's the largest number that's a multiple of the index 5 that is smaller than or equal to 22. So the 5th root of 3 to the 5th is a 3 outside. The 5th root of r to the 20th is r to the 4th outside. And I have the 5th root of r squared. as the leftovers inside. Okay, and then 38. Let's see here. 38 says, simplify each expression. If possible, the variables represent a positive real number. This looks like the ones we did for the other student. I think they're the same problems. Let me take a look here for just a minute. Yeah, it's the exact same ones I did earlier, so I'm not going to do those again, but we'll do 39. All right. And 39. Let's take a look at the picture. So hang on here. It says, first give the exact answer expressed as a simplified radical expression, then give an approximation rounded to the nearest tenth. Okay. It says, engineers have determined that 2 additional supports need to be added to strengthen a truss. Find the length L of each new support using the formula below and assuming A is 24, B is 16, and C is 12. Okay. So L equals the square root of B squared over 2, but B is 16. So 16 squared over 2 plus C squared over 2, which is 12 squared over 2, minus A squared over 4, which is 24 squared over 4. So let's take a look at the whiteboard screen. So let's see, L is, well, 16 squared is 256 divided by 2 is 128. 12 squared is 144 divided by 2 is 72. And let's see here. 24 squared is 576 divided by 4 is 144. Now, if we take 128 plus 72 minus 144, we get 56. 56 is 7 times 8, which is 7 times 2 times 2 times 2, or what, 14 times 4. And what I'm doing is breaking it down as a square of the leftovers. So we're going to get what, 2 square roots of 14. So that would be the exact answer, 2 square roots of 14. And then the approximation rounded to the nearest tenth. Okay. If I take 2 times the square root of 14, I get 7.4833147774, etc., etc. So rounding the 4, the 8 would round up, so 7.5 feet would be the approximate answer. Okay, that's all the questions that I had from emails from students. Any questions from anybody here before we go on to the next section? All right, then let's go ahead and proceed. So what I want to look at, first of all, what's the square root of 5 times the square root of 5? Well, I suppose the long way of doing that would be to say, well, that's the square root of 5 times 5, which is the square root of 25, which is 5. Isn't the square root of 5 times the square root of 5 equal to the square root of 5 squared? Because there's two identical factors. But what's the square root of 5 squared? Isn't that 5? My point is, we want to get used to going from here straight to there without having to go through these steps. It isn't wrong to go through these steps. It just makes it extra work. What about the square root of 13 times the square root of 13? That would be 13. What about the cube root of 2 times the cube root of 2 times the cube root of 2? Well, since I've got 3 factors of the cube root of 2, that would be 2. Any questions about that? All right, well, if there are, we'll find out here shortly. It says multiply and simplify. All variables represent positive real numbers. I've got the square root of 3 times the square root of 15. Now, there are a couple of ways I can do this, and how you do it, is up to you. But what I'm going to look at is, isn't 15 3 times 5? So wouldn't this be the square root of 3 times the square root of 3 times the square root of 5? But what is that? The square root of 3 times the square root of 3 is just 3. So I have 3 square roots of 5. Any questions about that? Let's look at another way of doing the same problem that you may or may not like. This would be the square root of 45, which is the square root of 9 times 5. And the square root of 9 is 3. So we get 3 square roots of 5. Again, they both work. Okay, how about this one? -3 square roots of 11 times the square root of 33. Well, that's -3 times the square root of 11 times the square root of 11 times 3, which is, -3 square roots of 11 times the square root of 11 times the square root of 3. But isn't that just 11? So I get -33 square roots of 3. Any questions about what I'm doing? Okay. As is often the case, life is going to get more complicated. 2 cube roots of 16 times negative the cube root of 4. Well, let's see here. That would be 2 cube roots of, I could take 16 and break it down to 2 times 2 times 2 times 2, but I'm going to break it down to 4 squared because now I've got, let's see, I've got a -2 cube root of what? 4 squared times 4, which is 4 cubed. So -2 times the cube root of 4 cubed, -8. Again, you see what I'm doing there? Is there anybody getting lost in what I'm doing? Okay.
I just got lost.
Okay. Let's back up a bit.
So right there.
Yeah. All right. So you're okay to there.
Yeah, I get how you got the -2 cube roots of 4 squared and 4.
So like that?
Yeah, so after that I got confused.
Okay. 4 squared times 4 would be 4 cubed, right?
Yeah.
What's the cube root of 4 cubed? 4 outside. Okay with that?
Yes.
All righty. Anybody else? Anything before we go on? Okay. Let's go on to the next example. The cube root of 3 times the cube root of 18. 18 is 2 times 9 or 2 times 3 times 3 or 2 times 3 squared. So this is the cube root of 3 times the cube root of 2 times 3 squared, which would be the cube root of 3 times 2 times 3 squared, putting them all together, which would be the cube root of 3 cubed times 2. Again, so I've got all my threes together. Okay, so far?
Yeah.
What's the cube root of 3 cubed? That's a 3 on the outside. And then I've got the cube root of 2 left inside. So what I'm looking for common bases that with exponents that I can put together to match the index. Okay. All right. How about this one? The cube, let's see, no, 3 times the square root of 8x times 2 square roots of 2x cubed y. So that would be 3 times 2 times the square root of 8x times 2x cubed y, which would be 6 square roots of 16x to the 4th y. So far, so good? You good to there?
Yeah.
Okay, which is 6 square roots of 16, which is a 4 outside, square roots of x to the 4th, which is an x squared outside, square root of y. 6 times 4, 24 x squared, square roots of y. So far, so good? Okay, how about this one? It says multiply and simplify. Again, all variables represent positive real numbers. 2 square roots of 7 times 3 minus the square root of 7. So we're going to distribute the 2 square roots of 7. So I get 2 square roots of 7 times 3 minus 2 square roots of 7 times the square root of 7. 2 times the square root of 7 times 3 is 6 square roots of 7 minus 2 times, well, the square root of 7 times the square root of 7 would be just 7. So we get 6 square roots of 7 minus 14. Any questions there? Okay. 3 square roots of 7t times the quantity 2 square roots of 7t plus 3 square roots of 3t squared. Okay. So distributing, I get 3 square roots of 7t times 2 square roots of 7t plus 3 square roots of 7t times 3 times the square root of 3t squared. This is 6 times the square root of 7t times the square root of 7t, but isn't that just 6 times 7t or 42t? Then this next expression, we get 3 times 3 is 9 square roots of 7t times, hang on here, times the square root of 3t squared, okay, which is 9 square roots of 21t to the 3rd. Actually, I'm going to take that and I'm going to leave it as t squared times t. I can't do anything to the 21, but that's going to give me a 9. The square root of t squared is a t outside, and inside I have the square root of 21t. So my final answer is that? Any questions there? Okay. Now we're going to FOIL some radical expressions because there'll be 2 terms times 2 terms. Again, all variables represent positive real numbers.
So on that last one, we wouldn't add the 42t and the 9t together.
That's like, okay, that's like 42x plus 9xy.
Okay, because it has
That's
the square root of that in there.
yeah, so they're
Okay.
not, yeah, okay. All right, let's see. So distributing the square root of 2 times the square root of 2 minus 3 square roots of 2 plus 1 square roots of 2 plus 1 times minus 3 is minus 3. Okay. The square root of 2 times the square root of 2 is 2. These are like terms. Minus 3 square roots of 2 plus 1 square root of 2 is minus 2 square roots of 2, and then minus 3. But these are like terms, so I've got -1 minus 2 square roots of 2. Or you could write it -2 square roots of 2 minus 1. Either way. Any questions there? Okay. How about this one? 4 cube roots of 9 minus 3 cube roots of 3 times 4 cube roots of 3 plus 2 cube roots of 6. All right, here we go. So distributing here, we get 4 cube roots of 9 times 4 cube roots of 3. Then here we get plus 4 cube roots of 9 times 2 cube roots of 6 minus 3 cube roots of 3 times 4 cube roots of 3, and then minus 3 cube roots of 3 times 2 cube roots of 6. Okay, so I've done my 4 foiling multiplications. Squeaky chair. All right. This is 4 times 4, 16. Cube roots of 9 times 3 is 27. But the cube root of 27 is 3 times the 16 outside gives us 48. Any questions about that? Okay. This gives us 4 times 2 is 8. Cube roots of 9 times 6 could be written as 9 times 3 times 2, which could be written as the cube root of 27 times 2. So what I'm doing is I'm going to take that 6 and pull it apart as a 3 times a 2 so that I can put this and this together to get 3 cubed or 27. So this is 8 cube roots of 27, which is 3, times the cube root of 2. So that's 24 cube roots of 2. Okay. Minus, so we're going to deal with that, 12 cube roots of 3 times 3 is 9, or 3 squared, so that 9 isn't going anywhere. because we can't simplify that. Okay. And let's see. We still okay? Still with me? Okay. Minus 3 times 2 is 6. Cube roots of 3 times 6, which is 3 times 2. That's not going anywhere either because I don't have a cube there. So that's going to be minus 6 cube roots of 18. And let's see here. None of those can simplify any further to where they're like radicals. So I've got 4 different unlike expressions there. Wasn't that fun? Noah is saying, yes, that was wonderful. Let's have more of those. Oh, well. How about this one? -3 cube roots of 10y cubed, the whole thing cubed. Okay. So we have a product raised to a power. So that's -3 cubed, the cube root of 10y cubed cubed. -3 cubed is -27. The cube root of 10y cubed, the whole thing cubed, would be 10y cubed, right? Because this and this would reduce down to 1/1. So now I've got -270y cubed. And let's take a look at this one. Square root of 3x plus the square root of 3, the whole thing squared. So that would be the square root of 3x plus the square root of 3 times the square root of 3x plus the square root of 3, right? You don't take that 2 outside and attach it to each separate term inside because there's terms inside, not a product. So foiling, we're going to get the square root of 3x times the square root of 3x plus the square root of 3x times the square root of 3 plus the square root of 3 times the square root of 3x plus the square root of 3 times the square root of 3. Well, the square root of 3x times the square root of 3x would be 3x. The square root of 3x times the square root of 3 would be the square root of 9x. The square root of 3 times the square root of 3x would be the square root of 9x. And the square root of 3 times the square root of 3 is 3. These are like terms. So I've got 3x plus 2 times the square root of 9x plus 3. I'll give you a minute to absorb that. If you have any questions on that one, let me know. Okay. Now, we've talked about simplifying radicals where you get everything outside the radical you possibly can. There's another process that's called rationalizing the denominator. And the idea being that not only do we want to kick everything outside the radical, but if we end up with a fraction inside, it'd be nice if we could rationalize the denominator, that is, get rid of the radical there and kick it outside as well, so that when we're trying to figure out what the square root of a number is, or the cube root or whatever, we don't have a denominator to deal with inside the radical. Well, let's take a look at this. The square root of 2 over 7. That's equal to the square root of 2 over the square root of 7, right? What if I wanted to rationalize, that is, take the square root of 7, which is an irrational number, and turn it into a rational number such as 7? Well, I could multiply by 1. The square root of 7 over the square root of 7. Isn't that equal to 1? So now in the numerator, I get the square root of 14, and in the denominator, I get the square root of 7 times the square root of 7, which is 7. I have rationalized the denominator, so I no longer have a fraction inside the radical. That 7 is beneath and not inside the radical. So this is called rationalizing the denominator. So in your final answer, there should be a rational denominator. Okay? Any questions about that? All right, let's take a look at another one. The square root of 5/3. So that's the square root of 5 over the square root of 3. To rationalize the denominator, we'll multiply the numerator and the denominator by the square root of 3. So we get that. Now be careful, okay? This is not equal to that. If we had this, we could reduce that down to the square root of 5. This 3 is not inside the radical, so we can't reduce it down with the 15. Okay. Okay, let's take a look at this one. 8 over the square root of 10. Now, the numerator is rational here, but I want the denominator to be rational. So I'm going to multiply by the square root of 10 over the square root of 10, which is going to give me 8 square roots of 10 on top and a 10 on the bottom. Now, I can't reduce the square root of 10 on top with the 10 on the bottom, but I can reduce the 8 outside and the 10 outside because neither of those are inside of a radical. 8 over 10 reduces to 4 over 5. So I get 4 square roots of 10 over 5 as the final answer. Okay, let's see here. Rationalize each denominator. All variables represent real numbers. So I don't have to worry about absolute value bars. I've got the square root of 15b squared over the square root of 5b cubed. Now, there are a couple of different ways I can go about this problem, and I'm going to explore them just to show you what's possible. One thing I could do is I could put them together, 15b squared 5b cubed. I could then reduce this down to what, 3, actually I'm going to get, I need a bigger radical there, 3 over b, because 15 over 5 is 3 over 1, and b squared on top, b cubed on the bottom gives me a b on the bottom. Now, what I want to do here is just make this a little smaller. Okay, so do you see how I got to the square root of 3 over b? So now we've got the square root of 3 over the square root of b. I'm going to multiply by the square root of b over the square root of b, which is going to give me the square root of 3b over b. Now that's one way of doing this problem. And there's nothing wrong with that way. Let's take a look at another way of doing it. Well, I could rewrite this as, let's see, b times the square root of 15 over, wait a second, I didn't write that correctly. This is supposed to be a 3. And then in the denominator, I'd have what, b square root of 5 over b, because the b cubed could be written as b squared times b, the square root of b squared kicks a b outside, okay? Well, I could even go further and I could take b times, let's see, the square root of 15 would be the square root of 5 times the square root of 3, and there's a b, square root of 5 times the square root of b. Let's see, what would that do? That would get rid of the b's and the square roots of 5s, and I'd have, oh, I just have this same thing, wouldn't I? And then I could go there. So, you know, is it better to put them together and reduce it like I did here, or simplify each thing separately and then put them together? I kind of lean towards this one, but they both work. Just be careful. Let's see here. The square root of 9x squared over the square root of 3x squared, excuse me, 9xy over the square root of 3x squared y. So that would be the square root of 9xy over 3x squared y, which is, let's see, that reduces to a 3, that reduces to an x on the bottom, and the y's reduce out. So I've got the square root of 3 over x, which is the square root of 3 over the square root of x. I'll multiply by the square root of x over the square root of x, and I have the square root of 3x all over x. Again, any questions there? Okay. One more example here. I've got 11, whoops, let's go with this. I've got 11 over the square root of 75s to the 5th. Well, one way I could do this is to multiply both sides by the square root of 75s to the 5th. Square root of 75s to the 5th. In the numerator, that'll give me 11 times the square root of 75s to the 5th over 75s to the 5th. Okay. Well, let's see. I could take this and take the 75 and make it 25 times 3, which is 5 squared times 3, and s to the 5th and make it s to the 4th times s. So then this would become 11 square roots of 5 squared times 3 times s to the 4th times s over 75s to the 5th, which is 11 times 5 s squared square roots of 3s over 75s to the 5th. Which is what? That'll reduce down to 1 over 15, and that'll reduce to s cubed. So I end up with what? 11 square roots of 3s over 15s cubed. So that's doing it by not simplifying the denominator first, by just multiplying the top and bottom by the whole thing. Okay, now hang on a second. Let's see, where did I get this from? Let's do this a different way. Okay, and let's say I've got this 11 over the square root of 75s to the 5th. And instead of multiplying the top and the bottom both by that entire radical in the bottom, let's simplify the denominator first. And this is going to be what? 5 squared times 5 times s to the 4th times s inside here. Which is going to be a 5s squared over the square root of 5, or excuse me, times the square root of 5s. Now, what advantage do I have here? Well, instead of multiplying the numerator and the denominator by this whole thing, now I just have to multiply by this radical part. So I'm going to have the square root of 5s on top, the square root of 5s on the bottom. That gives me 11 square roots of 5s over 5s squared times 5s. something tells me uh, 5s. Let's see if that's right. That's going to give me 11 square roots of 5s over what, 25s cubed. Yep, there's something wrong there, isn't there? How did I get a 15 here? I see what I did. No, 75, 5, 715. I don't know what I did. Somewhere I made a mistake there. Hang on. I'm going to pause the recording. All right, we discover the mistake. Right there, that should be a 3. Which makes that, oh yeah, that changes everything, doesn't it? Yep, okay. One little mistake and it all goes downhill fast. Okay, so this should be 11 over 5s squared square root of 3s. So now I'm going to multiply by the square root of 3s over the square root of 3s, which gives me 11 square roots of 3s over 5s squared times 3s, which is 11 square roots of 3s over 15s cubed. Okay. So once again, speed kills, right? But again, here you can multiply by the whole thing and then reduce things down, or you can reduce things down, simplify, and then multiply by a smaller one. My goal was to try and show you that this is easier, but I screwed it up. So much for showing you that, huh? All right. As I've often said to myself, slow down. With that, we shall stop the recording.